a metal and a non-metal. Here's the key idea. Metals always lose electrons, forming positive ions called cations. Non-metals always gain electrons, forming negative ions called anions. These oppositely charged ions attract, forming a strong electrostatic force, which is the ionic bond. Now, how does this ionic bonding compare to covalent bonding? If you remember from our covalent bonding video, non-metals don't like to give up electrons, so they share them instead. That's why covalent bonding happens between two non-metals. But in ionic bonding, metals are happy to give away electrons, and non-metals are eager to take them. This electron transfer creates ions which attract each other, forming a strong bond. Let's take a look at a real-world example. Table salt. Sodium is a metal with 1 electron in its outer shell. Chlorine is a nonmetal with 7 electrons. Sodium loses its 1 electron, forming an Na+ ion, and chlorine gains that electron, forming a Cl- ion. The Na+ and Cl- ions attract, forming an ionic bond. And just like that, you have sodium chloride or table salt. So, how can you tell if a compound is ionic? Look for these signs. It's made of a metal and non-metal. It has a high melting and boiling point. It conducts electricity when molten or dissolved. For example, table salt dissolves in water and can conduct electricity. But what about magnesium oxide? Let's break it down. Magnesium is a metal with 2 electrons in its outer shell. It loses both electrons to form Mg2+. Oxygen is a nonmetal with 6 electrons in its outer shell. It gains those 2 electrons to form O2-. The Mg2+ and O2- ions attract, forming an ionic bond. Now, let's test your understanding with some IGCSE style questions. Grab a pen and paper and try them out. Question 1. Potassium reacts with fluorine to form an ionic compound, potassium fluoride. A. Describe how potassium and fluorine form an ionic bond. B. Write the electron configuration of potassium and fluorine before and after bonding. Pause the video and give it a try. Here's the answer. Potassium is a metal with 1 electron in its outer shell. It loses this electron, forming a K+ ion. Fluorine is a nonmetal with 7 electrons in its outer shell. It gains 1 electron, forming an F- ion. The K+ and F- ions attract, forming an ionic bond. Now let's look at the electron configurations. Potassium is in period 4 and group 1. That means it has 3 fully filled shell and its outermost shell has 1 valence electron. So its configuration is 2, 8, 8, 1. After losing 1 electron, the fully filled shell underneath is exposed. Its electron configuration therefore is 2, 8, 8. Fluorine is in group 7 and period 2. So its electron configuration is 2, 7. After gaining 1 electron, it becomes 2 and 8. Question 2. A solution of sodium chloride conducts electricity, but solid sodium chloride does not. Explain why. Pause the video and give it a try. In solid sodium chloride, the ions are locked in place in a lattice structure, so they can't move. But when sodium chloride is dissolved in water or melted, the ions are free to move, allowing the solution to conduct electricity. Let's quickly recap what we've learned today. Ionic bonding happens between metals and nonmetals through electron transfer. Metals always lose electrons to form cations, nonmetals always gain electrons to form anions. Ionic bonds form due to strong electrostatic attractions between these oppositely charged particles. Ionic compounds conduct electricity only when dissolved or molten. What exactly is covalent bonding? Well, it happens when 2 non-metal atoms share electrons to achieve a full outer shell. Unlike ionic bonding, where electrons are transferred, nonmetals don't like giving away electrons. Instead, they share. Imagine you and a friend each have half a sandwich, but you're both still hungry. Instead of keeping your halves separate, you combine them to make one full sandwich. That's how covalent bonding works. Both atoms combine their electrons so they feel complete. Covalent bonds are strong and commonly found in gases, liquids, and solids. Alright, let's look at two important examples: methane, CH4, and water, H2O. Methane is made of one carbon atom and 4 hydrogen atoms. Carbon needs 4 more electrons and each hydrogen needs 1. By sharing, carbon forms 4 single covalent bonds, making methane a stable molecule. Water consists of 1 oxygen atom and 2 hydrogen atoms. Oxygen needs 2 more electrons and each hydrogen needs 1 more. They share electrons, forming 2 single covalent bonds. Remember, in covalent bonding, atoms always share electrons instead of transferring them. Now it's time to test your understanding with 2 IGCSE style questions. Question 1. Methane and oxygen both form covalent bonds. A. Explain why methane forms covalent bonds. B. Draw a dot and cross diagram for an oxygen molecule. Pause the video and try for yourself. Here's the answer. Methane forms covalent bonds because carbon and hydrogen are both nonmetals. Since nonmetals do not give away electrons, they share them, allowing each atom to have a full outer shell. Oxygen, O2, forms a double covalent bond because each oxygen atom has 6 outer electrons and needs 2 more to complete its shell. Question 2. Which of the following pairs of elements are most likely to form a covalent bond? A. Sodium and chlorine. B. Oxygen and hydrogen. C. Magnesium and oxygen. Pause the video and try for yourself. The correct answer is B. Oxygen and hydrogen, because they are both non-metals. Sodium and chlorine are a metal and a non-metal, and they would form an ionic bond. The same is true for magnesium and oxygen. Unlike ionic or covalent bonding, metallic bonding is the attraction between positively charged metal ions and a sea of delocalized electrons surrounding it. This unique structure gives metals their key properties. Let's take a closer look. In a metal, atoms lose their outer electrons, forming positive metal ions arranged in a lattice structure. The lost electrons don't stay with one atom, instead they move freely throughout the entire structure, creating a so-called sea of free electrons. These delocalized electrons hold the metal ions together with a strong force of attraction. This special bonding structure explains why metals have these 3 important properties. High electrical conductivity. The free-moving electrons allow metals to conduct electricity and heat easily. This is why copper is used in electrical wiring. Malleability and ductility. Metals can be bent, shaped and stretched without breaking. Their positive ions are arranged in layers that can slide over each other while still being held together by the sea of electrons. High melting and boiling points. The strong attraction between metal ions and the delocalized electrons requires a lot of energy to break, making metals solid at room temperature with high melting points. Now, how does metallic bonding compare to ionic and covalent bonding? Ionic bonding happens between metals and nonmetals, where electrons are transferred to form charged ions, like sodium chloride. It only conducts electricity when dissolved or molten. Covalent bonding happens between nonmetals, where electrons are shared, forming molecules like water. Most covalent compounds don't conduct electricity. Metallic bonding happens only between metals. Instead of transferring or sharing electrons, metals have a sea of delocalized electrons, making them great conductors in any state, which is why copper is used in wiring. For more information about ionic and covalent bonding, check out my videos. Now, let's test your understanding with 2 IGCSE style exam questions. Question 1. Why are metals good conductors of electricity? Pause the video and give it a try. The answer is metals have delocalized electrons that are free to move and can carry electric charge throughout the structure. These electrons allow electricity to pass through easily. Question 2. Magnesium and sodium are both metals. Explain why magnesium has a higher melting point than sodium in terms of metallic bonding. Pause the video and give it a try. Magnesium forms Mg2+ ions, while sodium forms Na+ ions. Since magnesium ions have a greater charge, they attract the delocalized electrons more strongly, creating stronger metallic bonds. As a result, more energy is needed to break the metallic bonds in magnesium, giving it a higher melting point than sodium.